Hey everyone, Mrs. Rogstad here. I'm going to show you how to do the data analysis for our volume and density lab. And this is a spreadsheet that I'm going to provide for you that you can fill in. And some of the main objectives of this exercise are number one, just learn in general how to analyze data on a Google Sheet. And number two, to insert formulas. And while that might seem a little bit redundant because we only have 5 samples here, no matter what you do in your life, you're probably going to need to keep track of data on a spreadsheet. And so if you have 1,000 pieces of data going down this column right here, using a formula is very powerful because you only have to enter the formula once and then it will do all the calculations for you. All right, so step one, we are going to place your measurements into the spreadsheet, and the measurements are going to be placed right here, basically. Now I want you to notice a few things. In each column I either put length or diameter, width or radius, and then height. And the reason for having choices is that you have some shapes that are cylinders, and in those cases you're going to be putting the diameter and the radius in those columns. And in the cases where you have prisms, rectangular prisms, you're going to be putting length, width, and height. Everything has a height, so that's what this column is. And then when it comes to the L shape, you're actually going to need to take up 2 rows for your data. One for the first leg of your L and the other for the second leg of your L, and then you're going to need to add them together. Also, I want you to notice that all of your data that goes in the spreadsheet needs to be in centimeters. Remember that you measured your data in millimeters with the digital caliper. So you should have those data points in your notebook in millimeters. And if you have not converted those numbers into centimeters, you will need to do that as you enter them into the spreadsheet. So remember that there are 10 millimeters in 1 centimeter. Therefore, we're moving our decimal point 1 space to the left. So if your, say, brass rod, the height of your brass rod, say you measured about 90 millimeters, that's going to be 9 centimeters. Okay, a couple other things that I want you to notice, very important. I'm not going to put CM into this column right here, or to the cell right here with my 9, because this spreadsheet is very dumb and it does not understand numbers and letters in the same cell. So in my column label, I have labeled it as centimeters, so you know that every entry in this column is going to be in centimeters. All right, so I have entered some numbers in here, and I just want to put out a disclaimer that these numbers are fake. I didn't actually measure them, and because of that, I don't have the right number of sig figs. So whatever numbers you put in the spreadsheet are probably going to have 2 or 3 sig figs, depending on what you were able to measure with the digital caliper. So depending on which digital caliper you used, you're going to write down every digit that the caliper gave you, and then move your decimal point 1 to the left to make it into centimeters. I'm only putting these numbers here as an estimate and to show you how to enter your formulas. Okay, so the first thing you'll notice is that for my rods, which are cylinders, I only have a diameter entered because that's the only thing I can measure, and I'm going to need to do a calculation to find the radius. Well, as you know, the radius is simply half of the diameter. And so to put this in as a formula, I'm going to click on the cell, enter the equals sign, and once that little question mark comes up, that's telling me I'm in formula mode. And so what I can do is click on the cell of the number that I want to use. So this is going to be diameter divided by 2. So I'm going to actually click on the cell because that's where I put the diameter, and then do divided by, which is a slash, 2. Enter or return. Okay, so see how slick this is. Now you probably could have done that in your head, I get that. But the cool thing is I don't have to re-enter the formula for the brass rod. So what I'm going to do is now click on this cell, and up here you can see that the formula is already entered. B4 means it's the contents of this cell. And the advantage here is that if I actually messed up my measurement, I could go back and fix it, and I wouldn't have to redo the formulas. The formulas would just recalculate according to that new data that I had. Okay, so to copy this formula and put it in another cell, such as the brass rod, I'm going to click on this cell, do Control C, and that's copy. And now I'm going to click on the cell where I want to replicate this formula and do Control V. And would you look at that? It automatically puts in the formula, but it knows to use the appropriate diameter, right? Because 1.5 divided by 2 is 0.75. So this is just really powerful. Imagine you had 1,000 pieces of data and you could just copy and then paste all the way down. It's beautiful. Okay, so now that we have this, we're going to enter formulas for volume. Now for our prisms, that should be easy because it's just length times width times height. So I'm going to click on the cell, do equals length times, and we're going to use the little star that's above the 8 on your keypad for multiplication. So I'm going to click on this cell times this cell times this cell, enter. Oh, and it gives me a suggested autofill. Isn't that so great? Now, in some cases, you do want to do the suggested autofill all the way down if you know that your formula is going to be the same all the way down. However, in this case, it's not always going to be the same because my formula for the cylinders involves pi and so forth, so I'm going to have to do those separately. So I'm going to reject this suggestion, but there may be other instances where you want to accept the suggestion. Okay, carbon steel bar is also a prism, a rectangular prism, so I can just do Control C, Control V, copy, paste. Now I get to my rods. Okay, so you remember the formula for the volume of a cylinder is pi times the radius squared times the height. So I'm going to do equals. Now in Google Sheets, the formula for pi is weird. You actually have to spell out pi, and then you have to do an open parentheses and a close parentheses. I don't know why that is. It's just whoever programmed this decided that's how we're going to indicate pi. Maybe so we don't have to hunt for a Greek symbol or something like that. Okay, so pi times the radius. Okay, now it's the radius squared, and squared just means it's the number times itself, so I'm just going to do times this number again. So pi times the radius squared times the height, enter. There we go. Okay, now if I don't appreciate the number of sig figs that are here, which is a fair thing, you can come up here to increase and decrease decimal places, and you can actually automatically have it rounded off for you according to how many sig figs you need to have. So I'm going to let you decide that for yourself. You know the rules for sig figs, but that's just a cool feature. All right, now I can copy and paste this formula for my other cylinder, which is very nice and handy. And then when it comes to my L shape, what I'm going to do is I have to do length times width times height, plus the other length times width times height to find the volume of that whole thing, right? Because I'm going to imaginarily cut my L shape in half and then add it back together. Don't really cut it in half in real life, guys. All right, so I'm going to put that formula here. So equals length times width times height plus length times width times height equals. And that should work. That should it should understand order of operations. All right, and so I'm only going to have one entry here that takes care of both of these rows because of the complexity of the L shape. All right, now mass, you should have measured this in grams. You don't have to do anything fancy with that. Just put in your masses here. Don't put the G for the same reasons. I don't have a good estimate off the top of my head for what these numbers might look like, so I'm just going to trust you to do that. All right, now this section right here is where we're entering our data for displacement, measuring volume by displacement. So in order to do this, you need to fill your graduated cylinder to a certain height. Let's say it's 60 milliliters. That's an approximation. You need to put exactly what your reading was for initial volume. But let's just make the assumption that I was really careful and I filled it to 60 milliliters for all of them. That may or may not work. I don't remember for the brass rod. You might have needed a little bit more in order to actually cover it. But you guys are the experts because you did this experiment today and I haven't done it for a year. Okay, so the volume of the object by displacement is the final volume minus the initial volume. So that's going to equal this cell minus this cell, enter. Oh, and now they're suggesting an autofill, and yes, this time I would love that autofill because it's the same formula all the way down. Okay, now for density, you know how you're going to find density, right? You can put in a formula, and it's going to equal this mass divided by this volume. And the reason I recommend using the volume of the object by displacement is it's probably going to be a little more accurate. Reason being is that some of these shapes are not a perfect cylinder, and there's even one brass cylinder in there, maybe you can find it, that the top is sawed off a little bit curved. You might have noticed that. And if there's any like dings or anything else, any other imperfections in that shape, measuring the volume by displacement is going to account for those dings and dents and imperfections, because the water is just going to cover it all up and fill it all in. Whereas when you're measuring with the digital caliper, yes, you're using this mathematical equation, but it's not going to account for the imperfections. It's going to assume a pristine, perfect shape. Okay, so to find the density, you're going to do equals mass divided by volume by displacement. And again, we're going to do suggested autofill. Okay, now this all says 0 because I didn't put in the masses yet, but you're going to have your masses, and that's going to be great. Okay, now your next step is to do the percent difference for the volume. And this is a formula where we are going to compare the volume that you got by measuring mathematically versus the volume that you got by a displacement. So you can see some of these are close, some of these are not. It's not real data anyways. Hopefully yours are closer. If you get less than a 15% difference, that's probably pretty accurate. But again, some of these factors you can't control. Some of these lurking variables you can't control because of the imperfections in the shapes and so on. Okay, so this is what the formula looks like. And you can look in the blue book for a nicer rendition of it. But this is going to be equals. And then I'm going to put an ABS, and that stands for absolute value, because we don't know which value will be bigger, and we want to just enter the formula as is. And then we're going to click on this volume minus this volume, close the parentheses, divided by this volume, and then times 100. And that should give us a percent difference, and yes, we do want to autofill. Okay, so I have abysmal results, except for the case of the aluminum rod, which is a case where I remembered what it was supposed to be very nicely. So you are aiming for a 10% difference is very nice. 15% or less. If it's more than 15% in your lab report, I want you to explain why you think that is. Okay, then you're also going to do a percent difference for the density. And that formula is nearly the same as this formula, except you're going to use a reference value for density. Now, I don't have this number off the top of my head. It is in the blue book. And I want to say it's page 195. I don't remember exactly. It's in the lab instructions at the end of chapter 9 in the blue book. And in there, there's a little table, and it tells you what the density of aluminum is supposed to be, what the density of carbon steel is supposed to be, and the density of brass is supposed to be. The density of aluminum would be the same no matter which aluminum, right? Because the L shape is also made of aluminum. So when you take the mass divided by the volume for any of the aluminum shapes, you should get a very, very close value for density over here. And then the reference value for density is what scientists have calculated over thousands and thousands of experiments, and it's just what's been accepted as the most accurate measure of the density of that material. So here you're going to do a percent difference formula. Again, it's going to be equals the absolute value of your density minus the reference value for the density, which you're going to find in that blue book, close parentheses, divided by the reference value for the density times 100. And hopefully this is within 15% difference. And if it's not, try to figure out why that is. And it could have been because you messed up a measurement. That's always a possibility. User error, right? So maybe talk with your lab group and see if any of those things apply. All right, if you have questions, you can private message me on Google Classroom, and I'll try to answer them. But hopefully this video will make it very clear what you need to do on this spreadsheet, and have a great day.